Some witchcraft.
So, well, good evening, everybody, and welcome to the Art Mixer. Tonight, we have Kevin's going to talk about OpAmps 2, and then after that, we'll have a roundtable. Of course, if there's anybody have any questions, concerns about whatever, well, don't be shy. So, I guess, Kevin, if you want to start up.
Okay, so let's see here. Oh crap, hang on. I'll share the screen first so I can see what I'm doing here. Start screen sharing, and let's do the entire screen.
It's been so long since you've done this, you've forgotten how to do
Yeah, no, I just got to find the right place. That's all. Okay, you should see my screen now. How's that?
You see, okay, there we go. That's better. Yep. That's good.
Okay. So anyway, I always like to start. Oh, what is this? Oh, there we go. Yeah. Got to make sure we got the attribution on there for XKCD. Sorry. My favorite comic. Anyway, OpAmps 2. And so what I wanted to do was just talk about a couple of different OpAmps. And maybe before, well, apologies to Dave. Dave, I'm going to borrow a few of your slides from your presentation, so hopefully that's okay. Just to kind of go over a couple of things. So, what are, just a little bit of a refresher, why do we have OpAmps, and why are they so useful? What were they good for? And as we were just talking about, it's back in the day when, when there was analog computers, right? The idea is that you would have an active unit with characteristics that, you could define the circuit by the feedback elements or the input and output elements instead of changing the amplifier itself. And so it makes it, sort of a universal building block, and you can define it by some passive components. And a typical ideal op-amp is this, right? And I know Dave's presentation will show you why this is exactly not true, but for the purposes of discussion, this is our ideal goal, right? Voltage gain is infinite, input resistance is infinite, output resistance is 0, and bandwidth is infinite. Now, you would never want to use an op-amp like this because it wouldn't be stable. It would be a great oscillator. But anyway. And the two amplifier inputs only respond to differential voltages. And there's an inverting and a non-inverting input, right? And it's basically a voltage-controlled voltage source. So any differential voltage causes a voltage output. And now I'm going to try to change over and drag Dave's presentation on top here. So let me see if I can do that. Oh, what did I do? Bear with me a second here. Okay, can you see Dave's presentation there?
Yes, we can.
Okay, good. All right. So just a couple of things, Dave talked about is, so just a reminder that, yes, a real op-amp is not perfect, and they don't always go to the voltage rails, which I think was what Dave was getting at here. But if you have a voltage at the plus input that's greater than the minus input, the output goes towards the positive rail. It tries to get there. And if the voltage at the minus input is greater than the plus input, the output's set to the negative rail, or it tries to get there. Not all op-amps can hit rail to rail, as they're known, or get really, really close. And so this is part of this controlling the circuit by external components, or in this case, no external components. If you bring a voltage on the signal input here, and this is the non-inverting input, then the output will go where it has to go to keep the differential voltage here minimal, or ideally 0, which means that this output voltage is going to be the same as the input voltage because it's non-inverting. So that's, standard voltage follower. And then you've got, an inverting amp and a non-inverting amp. So if you're coming in the negative input, the output tries to go to the opposite rail. Oh, sorry. First thing is that the non-inverting input is tied to common or ground. So it's at 0 volts. So the negative input also wants to be at 0 volts. It will do whatever, the output will do whatever it has to do to keep the negative input at 0 volts. So if you're coming in here with 1 volt and 1K, which is like plus 1 milliamp, then it wants to have negative 1 milliamp coming back here to maintain this virtual ground, for lack of a better term. So if you have 2K resistor here, that means you're going to have 2 volts at the output to create 1 milliamp, and it's going to be the opposite sign of the voltage at the input at the VN terminal. Non-inverting, similar situation, except it's allowed to be off of ground because you can put the voltage directly on the non-inverting input. And if you ask for 1 volt here, well, then it wants to have 1 volt here. So it's the ratio of these resistors, resistive divider here, that sets what the output has to go to maintain 0 differential voltage. So that's just a quick reminder, overview, whatever, that how these things are supposed to work. And this is just a summary of what I just kind of talked about. So since voltage gain is infinite and there's no current flowing into the terminals, even though there's a tiny little bit of current, the differential voltage is 0. The result is that the gain is determined by the external components for the most part. And for the inverting configuration, as it's drawn there, you tie the positive input to ground, and the input will do what it has to do to make that equation true, where minus RF is equal to RN. And I know you're using the LM324, Ian, but and I had to look this up. I thought, oh, okay, what's kind of a common op amp that you what is the 741 of 2025? And this one came up on some Google searches, an OP2323, and it's $2 at DigiKey. So it's not as cheap as the LM324s, but I've got all the data sheets, and I thought we'd just kind of go through them quickly at the end to show what's going on and what kind of state of the art, I guess, or what is common these days. And that's sorry, just continuing on here. So voltage output on the non-inverting is the feedback over the input resistance within the gain bandwidth product of the amplifier, which we'll come back to in a minute. And these amplifiers can do all kinds of stuff. As Ian was saying, they can sum, you can filter, low, high, band pass, integrate, differentiate. If you put a capacitor where the feedback is, you've got an integrator. You put a capacitor is where the are in, you've got a differentiator. So you've got function generators, you can make square waves, triangle waves, sawtooth, whatever. Comparators, precision rectifiers, sample hole peak detectors, on and on and on. They're extremely versatile. And if anybody has the OpAmp cookbook, which I have one from 1975, it's like 600 pages of OpAmp circuits and all that kind of stuff. So it's kind of cool. There's lots of things you can do with them. So, but that's one op-amp. That's the cheap and dirty one, the one that I was familiar with. I was kind of familiar with what this book called the OTA, or Operational Transconductance Amplifier. So this is one version, and it outputs a current proportional to the differential input voltage. So it's a voltage controlled current source. And then there's also this other neat thing called a current feedback amplifier. And its input is sensitive to current rather than voltage. So it's a current controlled voltage source. So we've got almost all the permutations here. The only thing we don't have is a current controlled current source. Anyway, so I thought I would talk about one example of each of these a little bit and go over some of the data sheets and just try to get a feel for what these can do for us. I'm not an expert on them. As I said, I tried to build the circuit using one of these OTAs and failed to launch, at least so far. So on an OTA amplifier, it's a little bit different because, so first of all, it starts as a standard op-amp. Just ignore these diodes here for a minute. But the output is modeled as a current source. So the I out is equal to the differential voltage times GM, or the transconductance, right? So many amps per volt. Or I out is the delta V in, so these two here, times GM. And GM is controlled by this current that you inject here. And these inputs will be at different, or can be at different voltages. It does not follow that sort of ideal amplifier rule exactly. And these diodes are here because they are used to linearize the inputs and reduce distortion. I'll leave it up to the reader to go look at the data sheet and figure out all the nitty gritty, but it's like you can use this input bias current also as a sort of pseudo gain control as well as this. So why would we want to do this? Well, so here's one thing that you can do is you can have an amplifier where you can control the gain by using a voltage. So you've got a voltage input. There's an adjustment to set the relative offsets of these to zero it out, I'm assuming. And then there's this resistor here, which is this bias, has a bias current from this input diode network. And because it's a current source, ideally the output resistance is high, or it's controllable, so it's high. But anyway, but you always need to have a load, right? So and it doesn't output a lot of current on its own. These things come in a dual SOIC pack. So there's like one amplifier, and there's this Darlington pair also built into the chip package. So you've got something like a buffer that you can bump the output current up. So the output voltage, since it's a current, is just I out times our load, this here, right? So the voltage gain is the delta voltage here times the GM times IABC, or whatever IABC gives you as GM, times the load. Okay, so that gets you a voltage in to a voltage out. Note that there's no feedback here, right? We're doing this without a feedback resistor. Just so that's the first thing that I noticed. And we used to use I don't know if anybody knows of the CA3080. It's like an old time original version of this sort of transconductance type amplifier. We used to use it as a multiplier. So you could put in a voltage here, and then with another voltage or current, actually here, you could multiply it, and it would act as an analog multiplier. It wasn't very linear because I don't think the 3080 had these diodes in the front. So there was some compromises at certain input voltage ranges. But anyway, so this is sort of a common one apparently, and an active unit that's available, and it's $1.84 DigiKey in single quantities. I think it's like $1.50 or $1.30 in quantities of 10. So that's one thing you can do, is you have a voltage controlled amplifier, and this is a chart. This is straight from the data sheet of your output amplitude versus your control voltage for this circuit. So if you can swing your voltage almost 25-ish volts, you've got a 30 dB gain range, which is pretty decent, I think, anyway. And theoretically, I think in the data sheet says somewhere that they can actually get 6 decades of gain if you really want. So this is, I think you can do better than this. So one good application for us, for those of us who want to do an AGC amplifier, this is straight out of the data sheet. But instead of using the ABC current to change the gain via the GM component, they take the output and you can adjust, you can set the amplitude that you're happy with. And then this buffer circuit just drives a low pass RC filter, which comes back and adjusts the bias on the input diodes. So as you get more signal here, it kills the gain here, and you've got a feedback loop regulating the gain. So I guess you'd have to these this RC time constant to be suitable for what you want. So that's a good radio circuit and fairly simple. Like I said, one chip, you could do 2 of these circuits. This is the one I tried to build, and I don't profess to really understand why this works. I think I do, but so it's a voltage controlled low pass filter. So by changing this voltage here, you change the current, and you change, according to this, the frequency that the low pass filter works at. And now, this thing can't run into megahertz like this. This is just a chart of the equation. That's nothing more than this. So, theoretically, with a GM of 1, you're, somewhere around 100 hertz, and a GM of 1,000, you're up around over 100 kilohertz. This would be, I think, cool and useful for, like a bandpass filter board. And I think the way it works is if you're bringing in, your time varying AC signal here, by controlling the amount of current going out, it affects the time constant on this capacitor, which determines when these turn on, which determines how much feedback current you have here. I don't know if anybody has a better explanation. Whoops. Sorry, I want to go back. Yeah. There is also, now I'm just going to get data sheet here because there's a, okay. So can everybody see the data sheet up there?
Yes, we can.
Okay. So this is what, this is what I was saying before. They're saying you can adjust the gain over 6 decades. Pretty good. And it's linear. 2 packets, sort of 2 complete sets per 16-pin SOIC package. And then, they've got, I've got a summary of some of the specs sort of at the end, but they've got a bunch of these circuits here. I picked a couple of them that I thought were interesting. And the amplifier bias, that IABC, is with respect to the negative rail. Just so you can see it down here, it's only like a diode drop and a junction drop away from the negative rail. So it's minus 15 all the way up to, I'm guessing, plus 15, or close to minus 15. Okay, why is it not showing everything? Okay, this is weird. It's like, okay, hang on. Let me just reopen that because it's not showing everything. Let's try this again. Okay, there we go. Okay, there's a whole bunch, there's an explanation there about what the linearizing diodes do and all that kind of stuff. You can use them as low as plus or minus 5 volts. I was running with plus or minus 12 because that's what I had. And you can run them up to plus or minus 15. And they're suggesting, like, so for instance, this circuit here could be used in like a stereo audio amplifier gain stage. And they're saying that they can the gain is matched within 0.3 dB. So that's sounds pretty good. low distortion, less than 0.1%. Oh, and okay, and here they say, yeah, minus 13. So just above the negative rail to the positive rail gives you 30 dB of gain. Now, I'm not sure how that gives you over 6 decades, because that's like the full range. Oh, no, hang on. That's this resistor, because that's setting the current, right? So they got this voltage controlled amplifier and then an equivalent circuit. So this is like that. So they had a stereo volume control, which, okay, that's neat. You can use one control voltage to set the gain on your right and left amplifier. An AM modulator, same thing. You can bring in your carrier in here and your modulating signal here, and that's it. Just straight math. A 4-quadrant multiplier. This was the circuit that we used to use on the 3080 back in the day to do some analog multiplication in control systems. So this was similar to what we used to have then. That AGC amplifier. You know what? Let me make this bigger here. There we go. This one is interesting, and I want to try this too. So, and there's a couple different variations of this, but by doing this, you simulate a resistor here, where your resistance is, you know, a ratio of these resistors here and the gain of the circuit or the current you're putting in for the signal to control the GM. And they have a singleted version, so reference to ground or common. The diodes. They also have a floating version. And I would love to just build this and just put an ohm meter on it and just see if it really does act like a resistor. You know what I mean? You need both packages to do the floating version, but as long as your voltage on the resistor can be within the rails here, plus or minus 15, this will theoretically act like a resistor. So anyway, I thought that was one of the coolest circuits they had available here. And then this low pass filter, there's also a high pass filter where instead of bringing low pass, you bring the signal in here. Low pass in here. High pass, you bring it into the capacitor. It'd be interesting to try both of them. And then they've got a voltage control, different filters, right? A Butterworth, low pass, a state variable filter. Let's see. Yeah, so here, like this, okay, they're saying this one goes from 200 kilohertz to 2 hertz. So that's, it looks like it has some decent possibilities for something, for, you know, a relatively cheap thing without having microcode or microprocessors and SI 5351s. A sinusoidal oscillator, like there's a lot of different applications, and it kind of goes on and on. Timers, a multiplexer, a phase lock loop, a Schmidt trigger. So anyway, very versatile. Tachometer, frequency to voltage in here somewhere, ramp and hold. Anyway, it just goes. Whoops. So I'm just going to close that one. So is there any questions so far or comments or anything? Because I can't see if anybody's.
Yeah, I'll watch for questions, Kevin.
Okay. All right. All right. So that's the operational transconductance amplifier. Let's see. Okay, I got to go back to. Whoops. Oh crap. Do this again, and okay. Then there's this other weird thing, and I don't, I haven't seen, I have never played with one of these. I just came across it, and there's a couple of articles I'll put some, when I'm done, I'll put some links in the chat so you guys can go off and take a look if you want. So this current feedback amplifier, where it's, you know, current difference input, right? Not voltage. So it's looking for a current on the input here. And then they have this feedback resistor here. And you use these two resistors together to set the gain and the bandwidth. And one of the differences of this amplifier versus like the standard, you know, the 324 or the 2323 OpAmp, like the standard voltage controlled voltage source, to make those the standard quote unquote OpAmp stable, they put a capacitor in there. So it's got a single pole filter. And that capacitor is what gives you your gain bandwidth product. In other words, the higher your frequency, the less your gain. Because that's what makes these things, or helps to make these things very stable, right? This doesn't have that in the same way. So you can set the gain and the bandwidth somewhat independently and still remain stable. And again, the slew rate, these things have amazing slew rate values. And this is one thing that I've seen, but I don't know, you know, just how important. But so if you have a feedback voltage source, wherever that's coming from after a buffer or whatever, this feedback resistor, they actually tell you what value to use in the data sheets, and they suggest you follow it. Do not deviate much, because it's really important, because it affects in the circuit, it affects this capacitor that they've got in there. And you're thinking, well, why would I want to use something like that? Well, so this is a driver for a twisted pair cable. And if you've got a lot of capacitance, right, which you might have on a long cable, and I'm not sure if they use these in Ethernet, or probably something similar for Ethernet drivers or something. But these things have huge output currents. It can drive a 10 microfarad capacitor, this particular one. And it doesn't care. It's got enough, it's got like hundreds of milliamps output to drive this. So they use these things to drive, you know, like for cables, buffers, video amplifiers, ADSL, so line drivers. Well, back in the day when we used to have dial-up, ADSL drivers. And this is, it's a poor copy from one of the articles I had, but so on a regular op-amp with voltage feedback, you can see this compensation capacitor results in this kind of gain curve, right? And if you want to run at, you know, 0.1 megahertz, you can get 60 dB. You want to run at 10 megahertz, you can get, you know, 20 dB or whatever. Not so much with this amplifier. You want to run 100 megahertz with 60 dB? No problem. And because they don't have that capacitor, that kills your gain at the higher frequencies. And so they can run at a much, much higher maximum frequency. And so this is just explaining what these charts are showing. This is a hypothetical one. It's not an actual amplifier, but it's to show the relative differences that the performance of these amps have. And you pay for it. It's $20 for this chip, a DigiKey. So now, hang on here. I want to get. Okay, so this is the, actually, hang on. So this is a comparison chart that I did. So the voltage controlled voltage source is the regular 2323. That's a $2 op amp. Transconductance amp 13700. It's like $2. And then this 3491 is whatever it is. What did I say? $20. So the input mode is voltage. Your typical offset from the data sheet is like that 150 microvolts. This one is like, I'll take plus or minus 5 volts with a 0.5 millivolt offset. And this one is just a current input. I should have looked at how much, but I didn't. The input impedance here, 80 gigohms, right? Here it's 26 kilo ohms. And this one's like 50K in parallel with 1.2 puffs. Input current, picoamps, nanoamps, microamps. So, okay, there's the input current. Slew rate, 33 volts, 50, 8,000 volts with a gain of 2. Obviously, you know, it will change as your gain goes up, but still, it's like, you know, 2 orders of magnitude greater than either of these other op amps. The gain bandwidth product here might be 20. There it's 2. This is 900 megahertz at 2 volts. 110 milliamps, 20 milliamps, 420 milliamps. And then your relative gains. Now, and obviously 125 dB sounds really good, but that's open loop and you can't really use it unless it's just a comparator or something. This one, they say adjustable over 6 decades, and this one's 50 dB for your small signal gain. So I'm gonna, yeah, I'll copy some of these links, but this is some of where I got the information. If anybody has an IC OpAmp cookbook, don't ever throw it out. It's a very useful OpAmp book. And then edn.com had some great articles. So I'll put those links up, and they talk about these different amplifiers and what you can do and what you shouldn't do with them and that sort of thing. So now, and where did I have, hang on, I had this data sheet. Okay. So yeah, and here's the data sheet for this 3491. So they're saying this 8,000 volts per microsecond can go up to 10 volts peak to peak, up to 100 megahertz. So that's pretty impressive, I think, personally. Some other, you know, applications they have here: power FET drivers, piezo element drivers, harmonic distortion. So dB down from carrier up to 20, 30, 40 megahertz is minus 80 dB down. So pretty good distortion numbers. And then there's a whole bunch of, a lot of that is just, these are just different voltage at plus or minus 15, plus or minus 5, 7.5, whatever, because the supply voltage has an effect on the slew rate and some of the gains. But yeah, normalized gain, and this is what they're talking about. See how they actually specify what resistors you should use here. If you want 10 volts per volt, you use this resistor, and then you change your G resistor to get the bandwidth. Anyway, so that's all I had on that. Other than ask questions, I'll try and answer them. And if not, maybe somebody else has some answers that has more experience with these. Because I have not used this current feedback amp, but it looks interesting. I just don't want to spend $20 to play with it. That's all.
Well, that's really good, Kevin. I enjoyed that. I picked up a few good things here. One is all those circuits you want to try. Boy, there's going to be, you could do a series of op-amp findings, you know, over the course of the next months, you know, with all those circuits.
Yeah, no, I know. And like the voltage controlled filters, I think that's extremely useful.
Oh yeah, and the other good thing too is those two of those op-amps you mentioned they're in the price range where you just order a bunch of them and experiment around with them. I have a couple of questions, then I'll get to the other guys. That's the advantage of you mentioned that Darlington circuit was within the package of the op-amp, but I noticed when you checked out a couple of different circuits, the values that I thought were inside the that package had different values.
Which values were you?
Well, like for example, when you were talking about the AGC amp, I think that was like 30K or something like that was the resistor value on that one, and then the previous slide it showed the resistor value was 100K.
Okay.
You know what I'm talking about? The circuit that's within the package, the Darlington circuit.
Yeah, yeah. No, that point, like that terminal is actually brought out. So it's bare. It doesn't have any resistance. So they're just showing that you would hook up a 30K resistor to that point
Oh,
on the
okay.
package.
Okay.
It's not, the resistor itself is not part of the package, but the
okay.
but that the Darlington is.
And one last one before I move on. The circuit you talked about, the voltage control resistor. What kind of do you recall what kind of values or what range of resistance it can control? Like 0 to 1 meg, or?
I'm just looking that up right now. Volume, voltage control resistor. Continuation of view. Okay. No, it doesn't really say, although it's R plus RA over GM. So let's say GM is 1, then like here they've got 100K for R. So it'd be 100, basically it'd be 100K. And if you could go up from 1 to 100,000, theoretically, you should be able to go from 100K down to 1 ohm, but just according to the equation.
Okay.
But I don't think that's practical. But and there is a capacitor in series there, so they're not talking DC resistance; they're talking, impedance, I believe.
Right. Well, the chip is cheap enough to experiment with, that's for sure.
Well, it is, and actually, I have 10 here because there's only $13 to get 10, so it's like I actually have some here, yeah, because I thought it might be useful for our backplane thing,
yep.
Bandwidth filter or whatever.
Mm-hmm. Well, that sounds good. Okay, got a couple of questions here for you. So Dave was up first.
Yeah, got to find my mute button. Yeah, Kevin, one of the things that with those voltage current feedback amps, yeah, I've had problems with bandwidth rolling off with the voltage feedback amp, and not just the bandwidth product, right? But with the voltage, the current feedback amps, I've never had them perform the way that they say, because they'll say, oh, it's good out to like 300 megahertz, and I found at like 30 megahertz it starts dropping off, the gain starts dropping off, or at 40 megahertz it starts dropping off. So I've never had much success with those amps. So I don't know if there's a trick or there's something. I guess you can't read my mind because you don't know what I did.
Yeah. So, well, did you follow their guide for like the resistance of the resistors in the feedback circuit and stuff?
Yeah, I at first I didn't, but then after looking at it, I realized they're quoting those values for a reason, because they even tell you what, how there's a pair, there's a voltage feedback. It gives you both values. However, the one thing it does, because I'm trying to drive this at 50 ohms, and most of them are for like 75 ohms or 100 ohms, because they're for coax cables or for twisted pair, which is 200 ohms.
Yep. Yep.
So I don't know if it's that's what's causing it.
What kind of gains were you trying to get out of it?
Well, just the standard, because I think it had a gain of like 10 maximum. Oh,
okay.
Like,
yeah. Okay.
Right. So even and that's 20 dB, and getting that. And Peter, you found probably the same thing with those 1253s, because those are current feedback amps.
The 1253, I had much more. I had not bad. I had good luck with that one. It was with the AD8008 that I had issues.
Was that a voltage? Was that a voltage or a current?
No, that was a current. That was one I thought it was a voltage. I wasn't even thinking a current op amp, but I was just messing with it, thinking it was a voltage op amp. But it turns out it was a current op amp.
Yeah, because I mean, even just looking at the spec sheet here, right? So plus minus 50, and you were using plus minus 15 volt supplies, right? I'm assuming, or whatever the chip was rated for that you were using. But I mean, if you look at this one here, a bandwidth for 0.2 dB flatness at 2 volts peak to peak, they've rated at 350 megahertz typical. It's like, that's pretty impressive. So like I said, I have not played, certainly not played with this $20 version of this current feedback amplifier, but it might be interesting to play around. I mean,
ask for a sample.
And the other thing, Kevin, the other thing I thought about, and I'm just pure speculation, because nowhere you see in these data sheets what the minimum voltage level is. Like, is it because we're maybe feeding in too low of a signal, or I don't know, because we're using them as a LNA, where you're feeding in signals really small.
Yeah, well, they are current amplifiers too, right? So like here, they're saying, so you can put in 10 milliamps into these inputs. Oh, hang on, is that supply volt? Yeah, and your differential voltage can be up to half a volt.
Yeah,
so yeah, I don't know what they do when you have like
that's maximum.
Yeah, that's maximum.
Yeah.
Yeah. But I don't know what happens when you feed in like millivolts. If you've got a really low gain, then
but Kevin, I was so happy to hear that your circuit didn't work, because half of my op-amp circuits don't work. So,
well, I mean, like back in the day when I used to do a lot of DC drive work, I mean, those things had gazillions of op-amps. Everybody used op-amps everywhere for everything. They were there was the speed loop in the drive. It was the current loop in the drive. It was the comparators for triggering the SCRs. It was like everything, right? They were just everywhere. So I'm pretty comfortable around regular op-amp circuits, and I know they work. But those were all kind of somewhat bandwidth limited, and it was not exactly a super taxing application either. These fancy things that they have now, it's like, if somebody had told me you'd have an op amp that could go to 900 megahertz, I would have said, yeah, right. It's just, so anyway, it's just new technology and very much more capable parts. But it wasn't $20 either.
The other thing I found out the hard way is that a lot of these amps, you got to pay attention to the voltage supplies, because just because it's got like plus or minus doesn't mean you could use it with a single supply, because some of these op amps will not work with a single supply. They just won't work. Others will, some won't.
Well, or you can use them, but you can't expect it to go down to 0 volts. It's not even going to get close to it. It might go down to like 2 volts instead of 0. And that's even from back in the day, right? Yes, that's true. If you want a rail-to-rail op-amp, you have to look for that as a spec, because they don't all do that. But just, that current feedback amp says it drives 10 microfarads. So this 2323 regular sort of standard op-amp, it drives up to 150 picofarads. It doesn't like high capacitance outputs, right? Because it changes that compensation capacitor value, and it affects that feedback loop. So this is and this is where some people get into trouble. You think, oh, I want to gain a 20 dB and I've got all this, but then if you've got a lot of capacitance in there, or you need a higher drive current, then that's not good either. And here it's like, see here, rail to rail input and output. So that's a spec on this one that you can. But you're right, a lot of them cannot. So.
Okay. You have another question, Dave, or do you want to think about it for a bit? I guess he's quiet now. Okay, Howard, you're up next.
Yeah, that was very interesting. I just had a question. Aside from ordering a PCB board for experimentation, what would be the best method to use to avoid impacting, the OpAmps behavior?
I know we all have had our bad experiences with breadboards. So, and that said, that's how I built mine. That doesn't work. It's on a breadboard. So, but it's also, it shouldn't, the capacitance shouldn't bother it because it's not this one. It's not the one that wants, something less than 150 puffs on a load. I wonder what I've never tried like ugly style or anything like that, but I don't know if that's practical.
So do you think that you kind of broke up there for a sec. So do you think capacitance would be an issue or not be an issue with breadboard?
I think it would be. Well, if you're just using a regular op amp, I think it could be, yes. Especially with these high performance ones. Yeah.
Yeah. So eliminating breadboards, then that's what I was thinking. What do you use?
Dead bug, ugly, or do the circuit boards like, these guys are all doing from, where's that one from, Ian? You're muted.
There you go. I got confused with my mute button with yours on the screen. Yeah, so that's just a 741. That's like the test circuit for the thing I'm building for this. It's just the proof of concept.
Is that from like JLPCB or something, or? No,
that's just like the proto board with a bunch of holes in it. Yeah.
Oh, okay. You just okay. That's a good idea.
Oh, I see.
Yeah, that's a thought.
Yeah. What you could do is get a breakout board, Howard, for the chip that you want to use, then plop it into the prototyping board that Ian just showed.
I see. Oh, okay.
And of course, boards are really cheap at JLC PCB as well.
Yeah.
Right, but there's the turnaround time. But I guess that's not as bad anymore, though, is it?
10 days, maybe. I guess.
Yeah.
That all it takes. Wow.
Yeah, I got mine pretty quick. The board I sent out.
Okay, thanks. Yeah, I forgot about those with the holes. Yeah. Okay. Yeah, thanks.
Yeah, I used to have some of those, but I don't. Maybe it's time to get a few more.
Yeah, you can get a whole kit, and they come with a bunch of different sizes.
Where'd you get that?
I don't know, Amazon.
Oh, okay.
It's an Elegoo double-sided PCB kit.
Oh, cool. Yeah, because I just, mine, the SOIC chip is just mounted on a breakout board, right? Or an adapter to get it to a dip package. So
I see. Okay, good. Thanks.
I mean, if you're going to mess around with audio circuits, you can probably mess around with a breadboard. But once you start getting up into HF, you're probably
and that's just it. Like if this thing really can run like at hundreds of kilohertz or megahertz, maybe that's why my breadboard circuit ain't working so good.
Yeah. Okay, thanks, Howard. Kevin, or not Kevin. Anybody else got any questions for Kevin? Comments for Kevin? Okay, Kevin. Well, I really enjoyed that, and you know what? You came up with some cool chips there. You did two presentations within one. Your cool chip segment, and
that's true. Yeah, I got to get back to doing that. I have a list of possibilities. I just have to.
Well, just what you went through with that, I thought as you were going through that first chip, the OP chip there, I thought, well, that's a pretty cool chip, and I thought, wait a minute, that used to be your thing at one time. Okay. Anyway, any comments for Kevin before we move on? Okay, thanks, Kevin. That was great.
Stop sharing. Yes. Okay, there we go.
Okay. Does anybody have any questions or inquiries to make about any of the projects they're doing or anything like that? Okay, let's go on to our usual mixer segment of the roundtable. Dave, you're up first. As if I didn't know what you've been up to, but go ahead for the group.
Did you say Dave?
Yeah, Dave as in Mr. OOI.
Okay, yeah, sure, yeah. What I've been doing is still working on my Z80 computer. I just ordered some new boards. I wrote built a new disk driver board, and I just ordered today. I just ordered from JLC PCB a front panel for it that's going to mimic the old Altair 8800 with panels and switches. So I've just ordered that. That'll be coming in 2 weeks, and then I've been working with Peter and Michael on the probe.
Okay, thank you, Dave. A labor of love, we'll call that probe. Next on the screen is Eric. Maybe Eric is still eating. You there, Eric? Okay, Howard, you're up next then.
Oh, did you say me?
I did, but looks like Eric. Okay, let's go back to Eric. We'll get him out of the way.
Okay, sure.
Yeah. Well, I'm easy because I don't have anything on the go other than trying to keep up with I don't know, whatever life. So yeah, nothing to report, unfortunately. So
Okay.
Yeah, pass. see you guys Saturday. How's that?
Yeah. Okay, Howard. I'm sure you're going to have a much more interesting report than the previous one.
Well, I don't know about that, but so I got distracted a bit from house things. But once I hit that capacitor, then I'm going to try the PA board again. So that's pretty well what I've been doing. But in the meantime, I decided to get a tiny SA to experiment with, and for hopefully once the T41 starts working, so I can see look at its output. So I've been playing around a little bit with that. So that's pretty well it.
Oh, okay. I didn't realize you went and bought. So you bought a tiny SA, did you?
Yeah.
Oh.
Yeah. It's interesting. I'm starting. I don't know a lot about them, but I'm starting to see the limitations that people talk about.
Okay. Okay. Well, then that's good. There's an awful lot on the subject. I bet you YouTube is full.
Yeah.
Of, so.
Yeah.
Okay. Great. Thanks, Howard. Hey, Ian, what's up with your neck of the woods?
Oh, still working on my simulator. I'm making good progress though. I've got this thing. I can actually drive it now. Lots of OpAmps in there. So I'm doing the KiCad circuit board design for my monitor. Now that I've got all the prototyping done, so I can read digital and analog inputs and output them over Wi-Fi to web page. Nice gauges, live data view. So now I'm trying to make the circuit boards up and get them sent out. So I got all the parts, so I know what sizes. So it's KiCad and form factors at the moment.
Okay, good.
And trying to clean up the wiring harnesses, so I don't need all.
Oh, that's what I thought you were spinning yarn there. Okay, you're making. Okay.
I don't know if you can see over yonder, but that mess of cables, I don't need all 200 of those. So now that I've got one of the real simulators, I'm stripping down the pin headers, and I'm going to connect just the wires that I need.
Cool.
Clean that disaster up.
Lots of fun. Good therapy in there, I bet.
Yeah, lots of stuff to work on anyway.
Yeah. Okay, thanks for that, Ian. Let's see. I think things got shuffled here. Oh no. Okay, Kevin. Well, we kind of know what you've been up to, I guess, but you do have some news from your end, don't you? What's new with you, Kevin?
Yeah. Well, I joined the Signaling Club.
Okay. Yeah, we start with Howard with the tiny SA, and then there's Kevin.
Yeah, then I went. Yeah, I decided I was going to join the Signaling SA Club and the Signal Generator Club. So, yeah, I turned them on. They both work, but I haven't done anything useful with them. So maybe on Saturday I can not blow them up. Although I did. Yeah, sorry.
You bought a SigGen as well?
A signal generator, yeah.
Oh, which one?
The 30 megahertz one.
Okay, nice.
And actually, I did hook it up to the scope because I just want to look. You know, the output is dirty, at least according to my scope. Like, is that normal?
Well,
I thought it would have very low. I thought it should be low distortion. It's like 14 bits, and
I can't remember the exact numbers because we got the same one, and it's better than my Agilent, and the Agilent's worth a few grand when it was new. And it's better, it's cleaner than the Agilent. So,
well, one thing I haven't done is put it on the spectrum analyzer because that'll tell me how clean it is, right?
Well, yeah, actually, I haven't looked at it on the scope. I've only looked at it under the SA.
So, but it's clean on there?
Yeah. Well, cleaner than the Agilent. I mean, there's
cleaner than the Agilent. Okay, so this is a relative measurement. Okay.
Yeah, there is a little bit of phase noise in there for sure. Dave's
yeah,
because
I could see it on the scope. It was like,
yeah.
Wow. Anyway, I thought it would have been better than that, but anyway, I haven't played with any of these new waveform generators, so maybe that's just the way it is.
Now you can measure; it'll keep you up at night. Dave, you got a comment for Kevin there?
Yeah. Hey, Kevin, was it on IZ or 50 ohms?
Yes. Yeah, it was on IZ.
It was on IZ. Now the way, I don't know if you know how IZ works. IZ maintains a voltage regardless of the resistance, the input impedance. So if you set it to 1 volt peak to peak, if you put, I'm exaggerating, put 0 ohms, it's going to put enough current to have that 1 volt. So it always locks in that voltage coming out, right? And also too, so you just got to be careful how you terminate it. The other thing is, what voltage level were you feeding out?
I was just like 1 volt, 1 kilohertz. Really?
Oh, simple. It should be fine. Yeah, that's
what I thought.
Yeah, no. Are you sure your scope was set up right? You had like on 10 times and all that stuff, and it was triggering okay?
Well, I'm gonna throw this all in a tote and bring it down on Saturday, and I just want to compare it because if I'm going to take it back, I want to take it back. If there's something wrong that I expect there should be. But
it's a good point that it could be a damage because with mine, I put mine in my SA, and I exceed the harmonic specifications. So it says something like, I can't remember, 60 something dBc or 80 something dBc, and I put it in my spectrum analyzer, and it goes below that.
Well, then either I've fat finger trouble, or maybe there is something wrong with it. But like I said, you guys know all this stuff and are familiar with it, so I can hopefully fairly painlessly kind of check things out and learn a little bit about it. And I gotta fix my DCR too because it's kind of deaf, as we discovered last fall. So I want to fix that. And I thought, okay, well, a good way to just mess around with the signal generator and the SA and get to learn how to use them.
Okay, very good. Al, you're up next.
Unmuted. Well, I don't have a lot to offer. As you know, I'm not doing a lot on the shack these days. But one thing I did order, GQRP, the British QRP club. I noticed this week they've got a PCB board kit for a transceiver kit for their 50th anniversary. Is it? So ordered one of those. So when it comes in, I'll do a show and tell and show you what it's all about. But well, it just seemed like an opportunity to get another kit added to the pile of kits that I haven't finished yet. Hi. Apart from that, life goes on, work goes on. Life is in the way, and work is a conflict of interest, don't you think?
Well, it looks like Kevin's figured that out. When are you going to figure it out and retire?
I haven't decided yet. I could have left a couple of years ago, so I don't know. It's I like the paycheck, and it's a reason to get up in the morning.
Gotcha. So's homebrewing. Okay. All right. Thanks for that, Al. Great. Hey, Bob, how you doing? Haven't seen you for a bit. What's new down in your shack?
Yeah. Nothing much here. I'm still in the process of relocating, so my shack is scattered in 2 different storage locations. So I'm kind of like radio inactive right now.
Oh, okay. All right. Well, thanks for the update there, Bob. That's good.
Did you guys go to Orlando? I meant to ask.
No, I didn't do Orlando this year. I'm not sure. You never know about next year, but depends if we haven't gone down to Florida for about 2 years now. So
Okay, are you going to Dayton?
yes.
Okay, I'll see you there.
Okay, great. That's look good, Bob.
Okay.
Hey, Bob, you can build in bed, you know. Bob,
Yeah.
you can build in bed, eh?
Huh?
You can build your kits in bed.
that's where I'm laying now.
Okay, I think we'll move on there. Charlie, good evening. What's new with you?
Hey, Peter. Not been very busy for the last while, and not a whole lot of radio stuff. Probably the most interesting thing I've done radio-wise is I started playing a little bit with JS8 call, which is kind of like FT8, but allows you to actually have a conversation with someone rather than just exchanging some very basic messages. So you can actually do keyboard to keyboard chit chat. So it's an interesting mode to play with.
Yeah, it's been a while since I've done some operating with the FT8s and like you say, JS8 call and stuff. But too much building. But maybe next winter. Okay, thanks, Charlie. Cherry, anything new in your neck of the woods?
Muted, Cherry.
No, we still can't hear you, but I don't see the mute sign. No, we don't hear you. Maybe come out and come back in again, maybe, Cherry. And we'll pick you back up when you come back in. Drew, good evening. How's your DCR coming along?
Well, good evening. Yeah, not built yet. How's that?
Okay.
Terrible. It's ridiculous.
How's your balloon then?
Balloon's coming along. I'm doing a lot of reading. They're hard to keep up with. They're a group of very dedicated people. And I no sooner to get some things read, and there's a whole bunch of amendments made to. There's a lot of development goes on. It's interesting. We'll see how it goes. I do have the kits. I got the boards all in some time ago, and the balloons and stuff. And yeah, I'm gonna have to just start trying to blow up a balloon just to see how they work. But it's hard to keep up with those guys. They're impressive. Other than that, played a lot with toroids.
Toroid fair.
Yeah, well, the thing is, the toroids that I'm playing with, I'm trying to cut back on some interference that I think I have in the shack between the computer, the Raspberry Pi, and my radio. I started to get some problems a while back, and so I bought the Amazon Bag O toroids, or ferrites, and started playing with them. I think I mentioned to you I went through a process of that YouTube video of how to test your toroids with a nano VNA, and so I found out a lot of interesting things. And I think I'm going to be able to cure the problem. But I also learned that I bought some Palomar common mode chokes that, they're not great. So it was quite an interesting learning experience.
Document it and then present it to us.
I have a PowerPoint I can send to you.
No, you can present it.
Oh, okay.
Oh, that's interesting. Okay, you buy these toroids and then you make an assumption about them, and now you can put them under test and just see how.
Well, that was the value of that YouTube. It really impressed me that another use for something I bought and didn't understand, and I gained a lot out of it. So it was interesting.
Okay, good. All right, thanks, Drew.
Yep.
Hey, Joe, how's things?
Guys, can you hear me?
Yes, we can.
Okay, perfect. Yeah, no, it's been a while. I've been tied down at work since falling into the new year. Nothing really new. I'm going to have to join Eric on this one. I haven't had a chance to do anything on my bench or do any operating. Where I left things last with Meshtastic and whatnot, I was able to get the boards that I've got communicating, like taking sensor data and actually putting it over the wireless. I'm just trying to get a center point up and running, the MQTT server. So that's where that's where I've got to pick it back up.
Okay.
Yeah.
Well, good luck going forward there then, Joe.
Thank you.
Okay. Good evening, Ken.
Good evening. Not much going on the bench at all. Actually, nothing at all. January, February, March is trade show months. So I've been to 3 trade shows, and we sold a lot of shit. And I'm working like 7 days a week now, so I have no time to do anything. The other thing is, hey Eric, did you hear back from Rex? Eric? No, I guess. The last time I brought up that kid I got from Rex, Eric started an email with Rex and wanted me to reply to what I thought about it. It was good. It was bad. No reply from Rex whatsoever. Nothing. So it's either he's ashamed, appalled, doesn't know what to say, or all above. So,
or he's all over. I usually find Rex spread pretty thin. Not to make excuses, but my experience with him is that. But anyway,
yeah.
Now maybe Eric will have a comment before the evening's over.
Yeah. Other than that, I haven't been doing anything at all.
Okay.
Work and sleep. That's it.
Okay. Thanks, Ken. Jerry, can we hear you now? No. I don't know what's wrong, Jerry, but
can you hear me now?
Oh, yeah, we can. Yeah.
Oh, okay. Seems like it is the webcam mic. Some reason it's not working, but it's going to the laptop mic now, so it's good. So nothing much on my side, but yeah, I've been looking at the group emails and trying to understand like what all people are doing, right? Yeah, outside of that, yeah, very busy at work, so kind of keeping up with the work, office, and not much of homebrew, but yeah, side by side, yeah, some reading is taking place. Yeah, that's all what is happening at my side. Thank you.
Okay.
And just one question, like the RF Pro PCBs, right? Yeah, I think some testathons are going on. This is one of the future projects for Buildathon, right?
Which project? I missed the first part of what you said.
The RF probe.
Yeah, eventually it will be, yes.
Okay.
Soon it will be, yes.
Yeah, great. Great to hear that. Thank you.
That's what we're working towards. Yes, the two projects that the two groups are working on, it's envisioned that they would eventually become a build-a-thon program. Yes. Okay. I guess I'm the last one there. Lots of stuff going on the bench, all basically related to the most of it's related to the Pro project, and then some of it's also with the backplane project. This afternoon, I needed a cable a little bit longer than what I had, and I had bought all these parts for SMA connectors and the cabling, and make up my own cable. Word of advice: just buy them already pre-made. It's not an easy thing to solder the SMA connectors on a piece of coax. I think I was successful, but it was not a pleasant afternoon. Other than that, you might have picked up, for those of you who are not aware, we're getting together at Dave's on Friday, Saturday. It's basically a GONAD, as it's the short form abbreviation. That's somebody, I'll let you guess at who came up with that one. Great One Night at Dave's is what's going on. And it's earmarked for putting the present configuration of the probe through its paces. A lot of testing and all that kind of good stuff. And so it should prove quite interesting. So if we're successful, then maybe hopefully we can move forward to the next stage with this particular project. Okay, that's it for me. Does anybody else have any other comments, concerns they'd like to bring to the table before we go?
Anybody hear from Frank?
I did actually. Now that you mention it, I sent Frank an email. I don't know if it was this morning or yesterday morning. I came across something that from his old company that he worked with, worked for about something there. So I sent it to him this morning, but I didn't hear from him back yet. I did actually have an email exchange just prior to the last meeting, and I can't. Anyway, he's still pretty tired and tapped out, so I'm not sure when we'll see him again. He's not sane, so I think he's really feeling the effects of his operations and all that kind of good stuff. But anyway,
yeah. The last time I emailed with him, he had just spent a couple of days in the hospital, and he got out, and he and Joan is his wife. Yeah, just got married.
Yeah,
that day. So, but he's going through a barrage of tests. So, but I haven't heard anything back from him.
he just says he's pretty tired and he can't stay awake for in time to meeting. He doesn't want to fall asleep in front of us.
Yeah.
Okay. Just had a message there from Eric. It looks like I got kicked out there or something. Got a message from Eric. Did you say Hassan was around? I don't see him.
Wow, I'm slow on hitting the mute button tonight. HM, that's him, isn't it?
No, that's Howard.
Oh, oops. Okay.
Well, now that you're back, did you hear Ken's question to you?
Yeah, I sent a message in the
chat. Okay.
There.
All right, so that's done. All right. Okay, so anybody else have anything they want to talk about? Okay, well, hearing none, thanks everybody for participating. That's great. And we'll look forward to seeing you next month, or not next month, in a couple of weeks. I think I'm up on for that one, so we'll see you then. Cheers, everybody.
Guys, thank you.
Have a good night, guys.
Good night. Thank you. Good night.
Right all.
Kevin, thank you again.
No problem. Thanks. Hey.